relates to your neurosim labs last week. And so, I screwed up in explaining the last part in my lab. When you're as smart as I am and been studying biology for over a decade, and, you make mistakes every once in a while. So instead of me just, trying to re-explain it to my lab, I thought it'd be kind of useful to explain to the whole class, because I'm sure there's confusion in the other class, if I had to guess. So here we have kind of like the spectrum of potential membrane potentials of a cell, right? It goes anywhere between positive infinity to negative infinity, right? And 0 is somewhere in the middle, right? And so if you go in this direction, you're increasing your membrane potential, and if you go in this direction, you're decreasing membrane potential. That's what it means when you're you're decreasing your membrane potential, right? Just meaning like the numerical value, is it becoming more positive, or is it going closer to negative infinity? Seems obvious so far. But let's say our cell is at positive 70 millivolts. That's their membrane potential. So when you have a membrane potential like this, if you move that membrane potential towards positive infinity, meaning away from 0, you say you're hyperpolarizing it. So away from 0 is hyperpolarization. So in this situation, increasing and hyperpolarization means the same direction, right? Now, if you take that positive 70 millivolts of membrane potential and bring it closer to 0, so towards the left in this example, that's depolarizing. So you're depolarizing membrane because you're bringing it closer to 0. In this situation, decreasing the membrane potential is the same thing as depolarizing the membrane potential. As long as you don't go past 0, they mean pretty much the same thing. But this means something very different when your membrane potential is negative. So, most resting cells are at a negative 70 millivolt membrane potential. This is, that's the kind of the situation we have in our cells. And so, once again, decreasing the membrane potential will take it to negative infinity, increasing the membrane potential will take it to positive infinity. But hyperpolarization and depolarization mean somewhat different things, right? Depolarization means you're bringing the potential closer to 0. So that means, in that situation, you're increasing membrane potential. A lot of people say, depolarization, that means I'm decreasing the membrane potential. It's not the same thing. Depolarization means you're bringing closer to 0. And the hyperpolarization means, in this situation, if you want to hyperpolarize a cell, you take it further away from 0. So in this situation, hyperpolarization is synonymous with, decreasing the membrane potential. So that's something you need to keep in mind. So increasing and decreasing mean you're taking your values to either positive infinity or towards negative infinity. Hyperpolarization and depolarization means whether you're taking it further or closer to just 0. Remember, 0 is kind of our neutral membrane potential. That means there's no difference in charge between the inside of the cell and outside the cell. So when you're hyperpolarizing that, you are creating a potential difference, a voltage difference we call it. And then when you're taking that voltage difference and bringing it back to neutral, you are depolarizing yourself. So I want to get some of the vocab out of the way, because when people are answering questions in neurosim, they'll interchange these words and they'll do it incorrectly. So just keep that in mind. But there's more to this review because I screwed up more than I thought I would. So how do we get to this negative 70 millivolt resting potential? And the way we get to that is looking at the electrical potentials of each of the ions in play. And so we have 3 ions in play. We have potassium, we have sodium, and we have chloride, right? And you get these potentials right here from the Nernst equation, right? And if this relates to our last review question, and if this still makes this, these numbers don't really make a whole bunch of sense to you, go back and review that. Still not making sense, come talk to me, talk it over. But at the very least, you should be able to figure out why this value is negative, why this value is positive, and why this value is negative. That's the thing I want you to take away from the Nernst equation, why these values have a certain sign, right? And so if you kind of combine all these electrical potentials together, because they're all in play at the same time, you will get your negative 70 millivolt resting potential. Now, you just can't add these together and get negative 70. If you add them all together, that would assume they all had an equal kind of weight to the resting membrane potential. But that's not the case. The reason that's not the case is because each of these ions have a varying level of permeability. For example, the potassium is the most permeable ion of these three. And it turns out sodium is the least permeable ion of these three. Putting chloride somewhere in a second. So they all have varying contributions, varying amounts of weight to what the resting membrane potential is. And that is described by the Huxley-Hodgkin, some guy's name with a K, equation. I don't know the three names. And you don't need to either. But that was the equation that kind of put the three together. And you can kind of look at the equation. You can review your notes from that lecture. The idea is, you take these electrical potentials and you multiply them by the permeability to kind of get what the resulting resting membrane potential is. All right. So, given that, one of the neurosym questions was about what happens when you add exogenous ions? When you're adding ions to the system that's outside the body. So you eat something too salty, or something else is going on. And the main punchline of those questions is if you increase the concentration gradient, increase the difference between the inside of the cell and the outside of the cell, as far as chemical gradients go, you are then hyperpolarizing your electrical potential. You can get that back from the Nernst equation, this equation right here. And vice versa is true. If you decrease your concentration gradient, you are then depolarizing your electrical potential. Keep in mind, I'm not saying the words increasing or decreasing. I'm not using those words. I'm using the words hyperpolarizing and depolarizing. So closer to zero or further away from zero. So if you can understand this, you can then answer those questions about what happens if you add potassium to the extracellular fluid. What happens if you add sodium? What happens if you add chloride? And so let's run through that right now. And so in order to understand these gradients, you have to understand what are the starting what's the initial conditions, we call that, of this cell. So right here, this is, ICF is intracellular fluid inside the cell. ECF is extracellular fluid, that's what's outside the cell. And these are kind of the disequilibriums we have starting out. You guys should know this. This is some information you can pull out anywhere. This is supposed to be common knowledge for you at this point. So what happens when you add potassium to the outside of the cell? So what happens is when we add potassium to the outside, this part increases, right? What does that mean for the concentration gradient, or the chemical concentration gradient? What does that mean? Are we increasing or decreasing it?
We're increasing it, we're moving it to zero.
We are decreasing the gradient here, right?
Or the gradient.
The gradient is going from this way, right? But if you increase what this side is, it kind of gets, it reduces that gradient, right? So if it was inside, it was this much, and outside was this much, and you bring up what's on the outside this much, you're reducing that difference, right? You're reducing the difference between the two levels. You're reducing the chemical gradient. And so, based off the statement here, if you're reducing, the chemical gradient, what can you expect from the electrical potential? Are we hyperpolarizing it, or are we depolarizing it? We're depolarizing it, right? So let me get rid of all this writing up here. So let's look at this. So the electrical potential of potassium was negative 90, right? So somewhere here, let's say. And we're depolarizing it. So we're moving it in this direction. All right? And so what that's going to mean for our resting membrane potential is it's going to get less negative, right? So for the overall membrane potential, it's going to get depolarized. right? So your example, uh, you can put this in a real life situation. Someone can be hyperkalemic. That means they have too much exogenous potassium. That's basically the situation we talked about. This would lead to basically almost infinite action potentials, right? Because the membrane potential is moved above this threshold value. That's what you kind of had to figure out in lab, right? And if someone suffering from hyperkalemia and they needed treatment really quickly, they said give them something salty, right? Something that has basically table salt, which is sodium chloride, right? So this is where I screwed up. And so I told my students when you add sodium chloride, or if you add more sodium system, you can hyperpolarize the cell. In this situation, I was actually wrong there. I screwed it up. And so I'll explain why. So if you add sodium to the ACF, right, what are you doing to the chemical gradient? Are you reducing the chemical gradient, or are you increasing your chemical gradient?
Increasing.
Yep, you're increasing it. You're increasing your chemical gradient. Right? And so if you look here, I started at positive 60, so say some. Oops, I put this in the wrong area. This is, we'll say this is where it is. So what does that mean? What are we doing to electrical potential? Are we hyperpolarizing it, or are we depolarizing? Or what? We're hyperpolarizing it, right? So we're taking this value here, and we're moving it in this direction, right? Hyperpolarizing, going away from 0. So we're dragging our total membrane potential closer to positive infinity, right? And so in a